Okay guys, so in this video we're going to talk about arc length. Now, arc length conceptually is actually not a very challenging thing. However, what makes it challenging is that we're dealing with square roots, and the integrals of square roots can be very challenging. One of the things we have is obviously our table of trigonomic substitution, so if we can have some perfect square, then we might have to deal with them this way, but really it's just a matter of we have to do quite a bit of manipulation to integrate square roots sometimes, and so they can be really challenging. But the concept itself, arc length, is really not too hard. But this is also why we learned Simpson's rule, is that in a pinch we can always use approximations to find an arc length. And it would be an approximation, but if that's all we have, then that's all we have. So, first of all, we do know how to measure the arc length of a circle, but what about more complex shapes? Now, as a reminder, an arc length of a circle would be something like, you know, the length here, right, of some angle, and that's pretty easy to do. But essentially, this concept here, this arc length concept, when we have more complex functions, is actually going to be based similarly to the ancient proofs of the circumference of a circle. So let me show you that real fast. So if you recall, or maybe you've seen this before, where if you're trying to approximate the circumference of a circle, you can just draw polygons inside and measure their lengths and get an approximation. And the more sides of a polygon we do, the closer and closer we get to the actual circumference. So we're going to use that same basic concept with curves, where instead of having this straight line here, we just draw a bunch of little straight lines to start approximating it. And so essentially, as we take this limit and go to infinity with it, we end up with the arc length formula. So if f prime is continuous on the interval a to b, then the length of the curve y equals f of x, that is the length of this curve from a to b, is the integral from a to b of the square root of 1 plus f prime squared dx. So this is our formula we're going to use. Essentially, we're going to take our function, derive it, square it, and plug it into this integral and integrate. We can also do this with y. Basically, if we're doing this with respect to y, if it's like a function in terms of y's, then it would just be a dy and f prime y. But generally, we deal with x's, so that's why we have this formula. As I mentioned before, because of this presence of this square root, we often end up with integrals that are impossible, or at least very difficult to integrate or to evaluate them explicitly, so we use approximation methods. But for us in class, right, we're going to pretty much be dealing with integrals we can integrate, unless there's some reason that we want to use Simpson's rule. But that's just kind of a construct of math class, because the reality is that these can be really nasty integrals very easily without proper thought put into the question. Okay, so let's find the length of the curve of this thing from 0 to 2. So first of all, let's take a look at this graph here. We have f of x is equal to 2/3 x to the 3/2. And we're going to do this from 0, so I'm going to go ahead and say 0 is less than or equal to x, which is less than or equal to 2. Okay. So we're looking for this arc length here. Now, if you notice, this is basically the hypotenuse of a right triangle, and so we can always use that to see if we're close. We can just kind of fit it to a triangle and get an approximation if we want. But let's take a look at this. So again, the idea here is we're going to take the integral from a to b, in this case from 0 to 2, of square root 1 plus f prime squared dx. Okay, so that is to say we need to find f prime or y prime, whatever. Maybe I could call this y prime. All right, so we need to find y prime first. So y prime here is going to be 3 over 2 times 2/3. X to the 3 over 2 minus 1 is going to be 1/2. So that's our y prime. Now, this is one of those things is we're now so set on integration that it's going to be kind of weird going back and doing some derivatives. But we are deriving this to plug it into our formula. So 3/2 and 2/3 cancels out, and we're left with y prime is equal to x to the 1/2. Okay, so that means that we have the integral from 0 to 2 of the square root of 1 plus x to the 1/2 squared dx. So that means we have the integral from 0 to 2 of the square root of 1 plus x dx. Now this we can do with either u sub or just basic integration. So that is to say, if we remember, we have 1 plus x to the 1/2, so we're just going to apply the power rule here. Okay, and because it's just a linear, we don't really have to use anything else. It's just basic u sub. Okay, so we raise this to the power, raise the power by 1, so that would be 1 plus x to the 3/2. And then we divide by 3/2, which is the same as times 2/3, but whatever. And then we divide by the derivative of this thing, which is just 1, so we don't have to worry about it, from 2 to 0. Okay, so that is to say we have 2/3 times 1 plus x to the 3/2 from 2 to 0. Okay, so if we plug in 2, 1 plus 2 is 3, so 3 cubed square root, right? So this would be 2/3 times the square root of 3 cubed, that's what that is, minus 2/3 times, in this case we plug in 0, 1 is just 1, that would be 1, so that's it here. So 3 cubed square root would be 2 square roots 3 times 3 square roots 3 minus 2/3. Which is to say, because again we pull out the squared, just leave behind that, 2 square roots 3 minus 2/3. This would be the exact length of this thing, which we can find as a value. So 2 square roots 3 plus minus 2/3 is going to be a length of about 2.79. Now, if this was, let's say this, well, we actually have this height, so 1.886, okay? Let's just do it as an approximation. If we had some triangle, 1.866, and we had a base here of 2, then we could find this length here by just taking the Pythagorean theorem, right? So square root of 4 plus 1.866 squared gives us 2.735. That's pretty darn close to what we ended up with. And so that would at least make logical sense for us. So that is our length. Okay, let's try another one. So find the length of this curve. We have this thing here. Okay, so first thing I'm going to do is I'm going to rewrite this. This is 1/3 x to the 3 plus 4x to the -1. Though that might be a little bit weird. So let's say plus 1/4 x to the -1. That's a little bit better. So we need to find our y prime. Again, it's the integral from a to b of square root 1 plus y prime squared dx. Okay, so our y prime here is going to be 3 times 1/3 is gone, so it's just x squared minus 1/4 x to the -2. Okay. Which we can also write as x squared minus 1 over 4x squared, whichever one we prefer. Okay, so it's the integral from 1 to 2 of the square root 1 plus x squared minus 1 over 4x squared squared. Okay, so with something like this, we're going to need to distribute or FOIL this out. So x squared minus 1 over 4x squared squared, that means we're multiplying them by itself. So that's like saying times x squared minus 1 over 4x squared. Okay, so x times x squared is going to be our x to the 4th. And then this thing and this thing would cancel the x squared, so it would be minus 1/4, and then we have it again, so it's minus 1/4 plus 1 over 16x to the 4th. Okay, so that means we have the integral from 1 to 2 of, so in these, if it's doable, we have, like I said, we have a few options. We have the table of trigonomic substitutions. This is not something we want to really deal with, this trig substitutions necessarily. I mean, we could potentially do it because we have a squared and it's a plus, so it'd be something like this. But that's maybe a last-ditch effort. I usually like to try and simplify our expression as much as possible, and oftentimes that will lead itself to something better. Okay, so we have 1 plus x to the 4th minus 1/2 plus 1 over 16x to the 4th. Okay, so 1 minus 1/2, that will be 1/2, plus x to the 4th plus 1/16 x to the 4th. Okay. Now, this is potentially, if I see a trinomial, one of the things I'm thinking is maybe it's a quadratic in form. So let's rewrite this thing into more standard form. X to the 4th plus our 1 over 16x to the negative 4, something like this, plus 1/2. Okay. All right. So what I'm thinking here is when I have something like this, I'm going, okay, well, maybe I can create this like perfect square via this thing. Okay, the other option is combining like terms. That's always another thing. So that is combine all of these fractions into one. That is obviously another thing that I am thinking. But if we could factor this, that would mean that x to the negative 4 is going to be like a u. And so u squared would be like x to the negative 8, so that's not really going to help us there. What would x to the 4th actually be for us? So if we raise this to like a negative 1, then that would mean x to the 4th is u to the negative 1, something like that. So then we'd have like a u to the negative 1 plus 1/16 u to the, or just u plus 1/2, something like that. That might be slightly better. It's a little weird to write something like this as our u and then a normal as a negative. But that's obviously something we might have to do. When I do integration or quadratic in form, I generally just think of this as my u, but maybe this isn't the correct move. So instead, I'm going to go elsewhere. But again, when I see trinomial, x's of different powers, I'm at least trying that thing. Okay, the next thing I'm going to go is, okay, well, what about just like x to the 4th being u? Then this would be a u plus 1 over 16u, like this, plus 1/2. Okay. Now, that is not really good enough probably still for us. It's still not a good form for us because, again, we're having issues with this square root. So the next option that I'm going to have is I'm going to combine everything. So these are not working out, and again, that is one of the joys of this stuff, is that sometimes you do some cleanup work and then you're just kind of stuck trying to deal with this thing and this mess that we've created. So anyway, so now I'm going to just combine these things. So this is like saying this is x to the 4th over 1 plus 1 over 16x to the 4th plus 1 over 2, right? So essentially 16x to the 4th would get common denominators between all of these. So this needs a 16x to the 4th, top and bottom. This needs an 8x to the 4th. Okay, so we end up with 16x to the 8th plus 1 plus 8x to the 4th. That's a little bit better. All over 16x to the 4th, okay? And that's inside our square root. Okay, now this is starting to look a lot better for me. So first of all, x to the 4th and x to the 8th, that is a squared to just a 1. Like if x to the 4th was our u, then this would be a u squared. So that's better. It might not be good enough yet still, but it's at least better. This thing here is a perfect square, so we can pull it out at least. So again, the square root of the whole is the square root of the top over the square root of the bottom. The square root of 16 is 4. Square root of x to the fourth is x squared. So that's out of the square root. Now we have the square root of, I'm going to write it in this form, 16x to the 8th plus 8x to the fourth plus 1. Okay. So now, if we think about this, maybe this is a perfect square. Okay, so let's think about this. 4x to the fourth plus 1 squared. If we think about this one, that would be 4x to the fourth plus 1 times 4x to the fourth plus 1. I think that should do it. If not, if I'm not sure, AC method factoring. 16 times 1 factors of 16 that add together be 8, 4 and 4, split it up. But I think I could actually just kind of see that one. So 16x to the 8th plus 4 plus 4x to the fourth is 8 plus 1. So that does check out. But again, we could use AC method to factor it. I just can see that perfect square here. Just a quick refresher, 16x to the 8th plus we would split, because again, 16 times 1, that's 16. Factors of 16 that add together to be 8, they are 4 and 4. So we split this 8x to the fourth as 4x to the fourth plus our 4x to the fourth plus 1, and we group them. So here they both have a 4x to the fourth. That leaves behind a 4x to the fourth plus 1. And here they don't have anything in common, so we say like a plus 1, 4x to the fourth plus 1. They both have a 4x to the fourth plus 1. We factor it out and leave behind 4x to the fourth plus 1. So it's a 4x to the 4 plus 1 squared. So that's what we have here. So again, I was hoping initially to be able to write it as a quadratic. I couldn't in that form, so instead I combined those fractions, and then I could. And these will nicely cancel out because we have the square root of 4x to the fourth plus 1 squared over 4x squared. These cancel, and we are left with the integral from 1 to 2 of 4x to the fourth plus 1 over 4x squared dx. Okay, now we want to integrate this. So how do we do it? Well, first of all, we might end up with a rational. This is technically a rational, and so you would divide it first of all, and then use your partial fraction expansions potentially. But this is a nice simple one since we have a monomial on the bottom. That is the integral from 1 to 2 of 4x to the fourth over 4x squared plus 1 over 4x squared, something like that, dx. So that is to say the integral from 1 to 2 of the 4's cancel, and we have x squared plus 1/4 x to the negative 2 dx. And now we can integrate this thing. So a lot of work, but it's just algebra. Not that that makes you feel better, but it's just algebra usually. Integral of x squared is x cubed over 3 plus 1/4 x to the negative 1 over negative 1 from 2 to 1. All right, so that means x cubed over 3 minus 1/4 x to the negative 1 from 2 to 1. Okay, now we can plug them in. 2 to the third is 8/3 minus 2 to the negative 1, that's 1 over 2, so that's minus 1/8 minus, okay, 1, that would be a 1/3 minus 1/4. So I'm gonna skip over the adding those things. I'm gonna do it on Desmos because I don't want to have to deal with that. Minus 1/8. That would be a minus 1/3 plus 1/4. And we get 59 over 24, which isn't a great looking number, but 59 over 24 is an exact number, and that is the length of this curve. All right, so again, my general concepts are, first of all, obviously, maybe table of trigonomic substitutions generally are A tangent theta. Maybe. The other option is factoring somehow. In this form, that's what I was trying initially, but that wasn't working. So instead, it's fractions, combine all of our fractions into a single fraction, and that's often a good move. To be honest, I probably should have started there, but they still had, when they have a trinomial like this, I'm still initially thinking quadratic in form, maybe. All right, let's do another one. Find the length of this curve. So we first need to find our y prime again. Y is natural log of 1 minus x squared from 0 to 1/2. So we're going to find our y prime. That's going to be 1 over 1 minus x squared times the derivative of the inside, that'd be negative 2x. All right, so that's our y prime. So that is to say y prime is negative 2x over. Now, this is not in a good form. You may think it looks okay. It's a difference of squares, by the way. That's another thing to note. That's a difference of squares, but it's also not in a normal standard form where like our x squared comes first. I like to move those first. So I'm going to rewrite this as negative x squared plus 1. And then I could actually clean this up a little bit more. I don't like to have the leading coefficient be a negative like that. So this is a negative 2x on top. But here, if I factor out a negative 1, that would leave behind x squared minus 1. And now I'm in a more standard form. So I usually like to do that a little bit because, I don't know, it just might make my life better in the future. So I just take care of it while it's simple. And the other nice thing is negative and negative makes it positive. So our y prime is actually equal to 2x over x squared minus 1. So that's a lot better. Okay, so we're going to plug it into our integral from 0 to 1/2 of the square root of 1 plus this thing squared. So 2x over x squared minus 1 squared dx. Okay, so now what we want to do is we want to FOIL this out. So that would be the square root of 1 plus 4x squared over, and I'm going to leave this alone, x squared minus 1 squared. The reason why is because it's already factored and is squared, and that will go out pretty nicely. But before we can deal with it, we need to take the square root of it, we have to combine these two things. So much like the previous one, we need to combine these two fractions. So this thing here needs an x squared minus 1 on the bottom, so it needs it on top. So 1 times x squared minus 1, that's just going to be x squared minus 1 plus 4x squared all over our x squared minus 1 squared. I didn't do that correctly. You need a x squared minus 1 squared. So we have an x squared minus 1 squared plus 4x squared. That's better. Okay. Square root, integral from 0 to 1/2 dx. Okay, so the bottom is nice. It will come out of that. The top, I need to FOIL that out. So we have the integral from 0 to 1/2 of the bottom is just x squared minus 1, which we could actually write as like x plus 1, x minus 1. I'm going to go ahead and do that now. X plus 1, x minus 1. We generally like them factored. Okay, now the top. X squared minus 1 squared, that would be an x to the 4th minus 2x squared plus 1 plus 4x squared. And it's still under the square root dx. So that leaves square root x to the 4th plus 2x squared plus 1 over x plus 1, x minus 1. The integral from 1/2 and 0 here, dx. Okay, now this is another one. It's quadratic in form. And so this would just be like, it's like if we said x squared was u, then x to the 4th is u squared. So basically we're dealing with a u squared plus 2u plus 1. And this factors as u plus 1 squared. So that is to say, what's our u? It's x squared. So that's x squared plus 1 squared. So integral from 0 to 1/2 of the square root of x squared plus 1 squared over our x plus 1, x minus 1 dx will give us these canceling. And then we have an x squared plus 1. Now this thing can't factor with anything. That's too bad. I was hoping maybe it would, but it doesn't. It doesn't cancel. So we have x squared plus 1, because it's not factorable, x plus 1, x minus 1. Okay, dx. Now, I factored this initially, but I generally like to have them factored just in case things cancel, but I can see clearly that it's not going to cancel. So in this case, I'm going to go back to its original form, which was our x squared minus 1, so that we can see what are we dealing with. We're dealing with a rational. What do we do with rationals? First of all, we check, are they the same power or is the top greater? It is. It's the same. So we have to do long division first, or synthetic division. If possible, we can't do synthetic division here, so long division it is. We're going to take our x squared plus 1, and we're going to divide it by x squared minus 1. Now, we usually need to have a placeholder, but because they have the same form, I'm going to survive without it. So, and you'll see that they'll still line up nicely. So, in order to get an x squared to be an x squared, we need to multiply by 1. 1 times x squared is x squared. 1 times negative 1 is negative 1. We then draw our line, subtract, and so we end up with these canceling, and we're left with 2. This is our remainder, so we'll say plus 2 over x squared minus 1. Which again is our x plus 1, x minus 1, which we're actually going to go back to in a sec. So now it's the integral from 0 to 1/2 of 1, which is easy, plus 2 over x plus 1, x minus 1 dx. So the reason why we did our division is so that we could split it up here. Now we are going to use our partial fraction expansion, and that is to say 2 over x plus 1, x minus 1 is equal to a over x plus 1 plus b over x minus 1. So that is to say, if we multiply everything through by our bottoms here, x plus 1, x minus 1, we get 2 is equal to a times x minus 1 plus b times x plus 1. So we can distribute 2 is equal to ax minus a plus bx plus b. Okay, so that tells us then a couple things. We know that a plus b, that is our ax plus our bx, will be 0 because there's no x term. And we also know that b minus a is 2. So a is negative b. So that would be b minus negative b is 2. So that means that 2b is 2, b is 1. If b is 1, a is negative 1. Okay, so we have now split this. So we are now dealing with the integral from 0. Wait, I can't even remember what it is. 0 to 1/2. There we go. We still have our 1 that we had initially here, this 1 after our first division. So now this is being split up into these two terms. So a is, so that's going to be plus negative 1 over x plus 1 plus b, 1 over x minus 1 dx. This is what we are integrating now. So integral of, we can now integrate this. Integral of 1 is x plus, well, in this case, I guess it's going to be minus 1 natural log of x plus 1. That's the integral of this. Plus the integral of this is going to be natural log of x minus 1. And we're taking it from 1/2 to 0. Okay, so 1/2 into here, 1/2 minus natural log of 1/2 plus 1 would be 3/2. Plus natural log of 1/2, which if you notice, the absolute values aren't necessary here in this stage, because these are okay, but we can drop them later. Minus 0 minus natural log of 1, which is 0, by the way, plus natural log of absolute value negative 1. Now obviously we need it for here because otherwise we want to have that, but negative 1, absolute value is 1, that would also be a 0. So we just have a 0 here. So we have 1/2 minus natural log of 3 over 2 plus natural log of 1 over 2. Which, if you think about it, we could actually clean this up maybe a little bit more. This is natural log, so minus natural log of 3 minus natural log of 2 plus natural log of 1 minus natural log of 2. That is to say, 1/2 minus natural log of 3 plus natural log of 2 plus 0 minus natural log of 2. And these natural logs are gone. That 0 is gone. We actually end up with 1/2 minus natural log of 3, which is a better form than what we had. And so I just use our log rules. If you remember, log of a quotient is the difference of those two logs. Okay. So nice and simple, right? There's a lot to it, but it's Again, it's nothing really new. It's just the same old tough integrations we've been dealing with. That's all. The only new thing is we do this. So the first step, and then do some combinations and stuff. Okay, let's do another one. Find the length of this curve. So in this case, we have a y squared equals x. All right, which is this thing here. Okay, now, if we want to find this curve, it's from 0, 0 to 1, 1. So we're dealing with this thing here. Now notice, what is this thing here? Like, we actually don't really even have to worry about this. So first thing we want to do is we want to solve for y. Y is plus or minus the square root x. That's what this thing actually is. But realistically speaking, we actually only care about the positive one of it. So that is to say, the square root of x. That is this upper portion. And so we're only really care about the square root of x, so that is y equals the square root of x from 0 to 1. That's really what we care about. Okay? So this is an interval, not a point. So to make sure that's clear, since we have points over there, I'll go ahead and rewrite this from 0 less than or equal x less than or equal 1. That's really what we're finding here. Okay. So that is to say y equals x to the 1/2. So y prime then is 1/2 x to the negative 1/2. And we're going to throw this into our formula. We have the integral from 0 to 1 of the square root of 1 plus 1/2 x to the negative 1/2 squared dx. Okay, so x to the negative 1/2 squared would be x to the negative 1, so the x on the bottom. So we have the integral from 0 to 1 of the square root of 1 plus, and 1/2 squared is going to be 1/4, and x is on the bottom like here, dx. So that's how that simplifies, nice and clean comparatively. We're going to now combine these things. These are two fractions. Let's combine them. This needs a 4x, top and bottom. So we end up with the square root of 4x plus 1 over 4x. Integral from 0 to 1 dx. Okay, so something like this, we could obviously split back up to this thing if we need. But as is, in this form, this is not super great. Like, this isn't a super excellent form for us. So we're going to have to be maybe a little bit clever here. So we could potentially pull out the 4 if we need. That wouldn't necessarily do us well. But basically, that is to say, this is like the square root of 4x plus 1 over like 2 square root x, something like that. So we have that available to us. Maybe if we rationalize this thing, so that is if we multiply top and bottom by this, like square root x, maybe that will make things better. Maybe it won't. I don't really know. The problem here is that this isn't like some perfect square here, so that's kind of problematic. And again, that's kind of the issue we're running into here. Is it's like, okay, well, how do we deal with this thing? Now, another option is I did it for the x, right? But realistically speaking, I could also treat it in terms of y, which I might have to do because this is something that I don't really know if this is going to clean up. I mean, we could try really quick. Multiply by square root x. That will give us the square root of 4x squared plus x over like 2x. But again, that's not really making our lives any better. This hasn't changed anything to be like I don't know, like a difference of squares or something factorable. I mean, you could pull out an x, but again, that's not really doing us any good. So we may need to revisit this. So even though we could certainly write the portion we care about in terms of x, maybe we need to think about it in terms of y. So that is to say, think about it like this. X equals y squared. So the integral from, if we want to change it to dy, we can. Now we're talking about it in terms of y. So in terms of y, this is from 0 to 1. And it's square root of 1 plus x prime squared. So let's go ahead and try that out. Maybe things will be better. I'm not going to delete any of this stuff, but let's just pull it into another page just in case we need to come back to it. Let's copy this. Okay, and we'll use this. So in this case, we're doing it in terms of y because that x really wasn't panning out for us. So maybe we should try it in terms of y. And again, it just means changing, like we're now calling it, instead of y prime, it's x prime, and treating it as a function of y. And so we integrate with respect to y, and we do it along the bounds of our y-axis from 0 to 1, which happens to be the same as the x-axis, but don't be confused by that. Maybe I should have written a better problem if I didn't want you to be confused by that, but oh well. Okay, so let's find what x prime is. X prime is 2y. Okay, so we have the integral from 0 to 1 of the square root of 1 plus 2y squared dy. Okay, so we have the square root of 1 plus 4y squared dy. Integral from 0 to 1. Okay, now this is not something we can factor. This is not something we can combine as fractions because it's not a fraction. So we're going to go over to our trig substitutions then. This is a perfect square. We're doing it in terms of y's, but it's the same basic concept again. So we have essentially our x here. If you think about it, that's really 2y squared. 1 plus 2y squared. So that's kind of like our x term in our trig substitutions, and our a is 1. Okay, so that is to say, we're going to say that 2y is equal to tangent theta. 2y is tangent theta. So if you remember, we have a triangle, it's theta. So tangent is opposite over adjacent, so this is 2y, this is 1, this is the square root of 1 plus 4y squared. That's our triangle we're dealing with. Okay, so if you recall, what we do with this thing, we need to kind of like derive this thing and deal with our dy, right? So if we bring that 2 over, we have y equals tangent theta over 2. So that means dy is equal to, the derivative of tangent is secant squared theta over 2. Okay, so we have our dy, that's going to be replaced. We have our 4y squared will be replaced with this. So we're going to go ahead and do our substitutions now. So this is the integral. Now because we changed our bounds of integration, or we change this from dy's, we're changing it into theta, we can change this bounds of integration as well with this conversion. So tangent of 0 is 0. Tangent of 1 is something. I guess I have to think about it with my unit circle. It's like, I don't know, square root 3 over 2 or something, who knows. All right, so we can go ahead and do that though. So again, this is 0. Tangent of, okay, never mind, I'm sorry. I was kind of messed up with my bounds of integration, but since we're doing all this like substitution, that's why I'm kind of doing it. We're basically going to use this. Our y is here, so essentially we could say something like, if we want to change it, we would say 2 times 0 is tangent of theta, and we want to know what's the theta then. So 2 times 0 is 0, so tangent of theta would be 0, so that would be tangent inverse of 0 is theta, which tangent inverse of 0 is 0. We kind of knew that one. So that's going to be so this would then be 0 in terms of theta. And then we need to do the same thing for 1. So we'd have 2 times 1 is tangent theta. And so that would be tangent inverse of 2 is theta. So it's not anything nice. That's too bad. Nope. No. Anyway, it was worth a shot. You know, you never know. So it's definitely a root of some sort, and I'm not going to mess around with it. So since I can't really find it, I could call it this like tangent inverse a 2 if I really wanted to, but it's probably not going to be really worth it. So that was kind of a situation that maybe, it's not going to be worth it. So we'll at least have that if I need to, but for the time being, I'm just going to remove my bounds of integration while it's in terms of theta. Okay, since I couldn't think of something really nice in it, and I'm sure if I spent a little bit of time I could find it, but because again, I guess if you think about it, like 2 is tangent is sine theta over cosine theta, so that would be 2 cosine theta is sine theta. So you know, that's one thing that we can think of, like when would this be that? But I don't know. I can't really think of anything, so I'm not going to waste any more time with it. Okay. If I spend a little bit of time, I'm sure I can find it, but I don't really care enough. Okay, so again, the changing of bounds of integration is only there if it's going to make my life better, not worse. Okay, so from 0 to 1, again, we now just not having any bounds because we're going to go in theta. This is going to be the square root of 1 plus. Now, 2y squared would be tangent squared theta. And then dy is going to be secant squared theta over 2. And it's technically a d theta here, so d theta. So we're now in theta. Okay, so 1 plus tangent squared theta is maybe fine as is, because we could write this as like secant cubed. But if we also think about this as like tangent theta, or this would be a secant squared, I think. Let's go to the trig cheat sheet real quick. So 1 plus tangent squared is secant squared, so we can make that a secant cubed over 2. But what if we said tangent of theta is u? And then we could say that like du is secant squared theta, d theta. And then we'd have the integral of 1 plus u squared. And this would be a du. Now the problem is 1 plus u squared would be its own like trig stuff. So actually that's not gonna really play out nicely for us. We can also go to the table, but I have some other plans for us. Okay, so 1 plus, we're gonna go ahead and write this. I was thinking maybe it would make it better, but 1 plus u squared, the square root of that, is just another like integration substitution, and it's really not gonna make our lives, I don't think, any better. I guess it could, because we have, let me see. Let's see. I have this like more simplified one. So here, just the integral of secant we can always find with this thing. So I guess we could do a further substitution. Ooh, that would be ugly. I really don't want to do that. We could do it, and then it would just be a secant. And we have the table for it. But instead, I'm going to do another one that's also going to be bad. So you're going to be like, ugh, I don't like either of these. Well, oh well. Okay, so rather than doing that u, let's go ahead and write this as the integral of secant squared square root theta, secant squared theta over 2 d theta. Okay, so that means that these cancel, and we're left with the integral of secant theta times secant squared theta. I'm going to pull that 1/2 out, d theta. Okay, that is to say secant cubed, but here's the problem, is that secant cubed integration is kind of a challenge. So we're actually going to treat this as like an integration by parts, because the other one really wasn't working out for us. So if this is going to be like our u is secant theta, then our dv is going to be secant squared theta. And you might say, why am I choosing that? Well, because the integral is easy. So v is tangent theta, and du is going to be secant theta tangent theta d theta. Okay, so this is 1/2 times uv, so that's secant theta tangent theta, minus the integral of v du. Tangent theta secant theta tangent theta d theta. Okay, now the derivative of tangent is secant squared. The derivative of secant is secant tangent. So basically, we have this 1/2 times secant theta tangent theta minus the integral. So we can write this as like tangent squared theta secant theta d theta. Now, what is tangent squared? Well, that would be secant squared minus 1. Let's see. Tangent is secant squared minus 1. Yep. So secant squared theta minus 1 times secant theta d theta. And it's still 1/2 times the secant theta tangent theta. Okay, now if we look and multiply this in, this would be minus the integral of secant cubed theta minus secant theta d theta. We could distribute this negative as well if we want to like split this up into two integrals. You might say, ooh, that's not good. We're back to where we started. But if you remember, that's actually not so bad. So if we call this like plus the integral here, because again, it's minus and a minus, that distributes as a plus. So we have these two integrals now. And we still have like 1/2 times all of this thing. Theta, tangent theta. So let me go ahead and distribute that 1/2 as well. So that's 1/2 secant theta tangent theta minus 1/2 times the integral of secant cubed theta d theta plus 1/2 times the integral of secant theta d theta. And keep in mind, this is all equal to the integral of what we were starting with here. This thing here, 1/2 times our secant cubed theta. That's what that thing here was, okay? So if I add this over, 1/2 and 1/2 makes 1. So I'm going to add this secant cubed theta, this 1/2 secant cubed theta over, and we get the integral of secant cubed theta is equal to 1/2 secant theta tangent theta plus 1/2 times the integral of secant theta, which I'm going to go to our secant theta here. It's natural log secant theta tangent theta. So natural log of secant theta plus tangent theta. All right. So that's what this thingy is. So if we're looking for, back up here, this thing, that's what the integral of this is, and it's 1/2 of that. So if we want 1/2, which is what we had, that just changes this to 1/4. So we have 1/4 secant theta tangent theta plus 1/4 natural log of secant theta plus tangent theta. Okay, which again is pretty ugly. But don't worry, we're not quite done, because now we have to convert our thetas back into our u's or our y's or whatever. Okay, so if we recall, we have this this thing here. So let's go ahead and bring that triangle down to replace all these things with them. Okay, so secant. Secant is 1 over cosine. Cosine is adjacent over hypotenuse, so it's hypotenuse over adjacent. So that is 1/4 times the square root of 1 plus 4y squared over 1 times tangent is opposite over adjacent, so that's times 2y plus 1/4 times natural log of secant is again this, so square root 1 plus 4y squared plus tangent is just going to be our 2y. Okay, and we're doing this on our y from, what was our original bounds of integration? 0 to 1, okay. So that one was pretty ugly, and we're not quite done, but it is what it is. All right. So let's go ahead and start plugging these in. I hate to screw up here. 1 into here for y. That's 1/4 times the square root of 5 times 2 plus 1/4 times natural log of 5, square root 5 plus 1, plus 2, excuse me. There we go. That would have been a bad one. Minus. Okay, now let's do it again for 0. So 0 makes this, well, it makes this 0 times everything. It's going to be 0. And 0 here would make this, so this would be plus 1/4 natural log of 1 plus 0. Natural log of 1, that's 0. So we're just here. So we end up with the 2's here will cancel. And we get square root 5 over 2 plus 1/4 natural log of square root 5 plus 2. And we could drop the absolute value because this is clearly positive. Whew. All right. That one was bad, right? But again, it is what it is. I mean, these integrals are bad. But the actual arc length itself is not bad as a concept. So in this case, notice we actually stuck with just x prime here. So we changed it. Instead of calling it from along dx, we're going to do along dy because that was easier. Not much easier, but at least we could find the integral. I couldn't find it elsewhere. Now, this secant cubed is one of those ones where it's like, oh, you had to be kind of clever. And so that's why I'm bringing it up, is because it does show up sometimes, and it's like one of those things. The tables book of integrals has it, but I don't really know it off the top of my head. And the table has a lot of stuff. And to be honest, you should be practiced in not using that table. Basically, the initial portion of that table, the basics, this is all you really have to go off of. This is what you're usually given out of being kind. Okay? If you notice, it's called Calc 2 exam sheet. It has that. That's it. And it also has the some trig stuff. Anyway, let's talk about one other aspect of this. I'm not going to spend too much time on it because I don't care that much about it, but it's worth noting. And that is, we can use what we know about finding the arc length to find a function that measures the arc length of a curve from a particular starting point. So basically, the function, this is s of x, so this will be in terms of x, from a to x, is the square root of 1 plus f prime of t squared. So basically, we think about it in terms of t. So we're doing the same basic stuff. The only difference is basically at the end, we're going to take it from some bound from a unknown value to x, an unknown. So basically then we can just plug in any value for x and find how long would it be at this stage? How long would it be when x is this, etc. That's all it's really doing. So find the arc length function of this curve. So again, if we call this y in terms of t now, so this is 1/2 t squared, okay? Our x is our initial starting value, so that is from 0 to x is what we're going to be integrating this. So this is s of x, the distance, the length of x of our function. The length of our function in terms of x will be the integral of 1 plus y prime of t, just some other variable, squared dt. dt. So we just find some other variable. Realistically speaking, we only do that so we don't get confused in our x's of like, what can we replace now? So we just do it in some other variable. It could be anything, choosing t in this case. So y prime is going to be t. That's what y prime is. So we have the integral from 0 to x of the square root of 1 plus t squared dt. All right. So we're here. Okay, now, just to save the hassle of it, let's see, the book's table of integrals. Okay, this is the square root of 1 plus t squared that we're integrating from 0 to x dt. This is surely in the table. Let's take a look at it. I know I just got done saying we don't really want to do that, but I know this video is getting a little long, so I'm just going to find this one. So square root, we need a square root with a plus. So here's a square root with a plus right here. Okay, a squared plus u squared is u over 2. So let's go ahead and write that one. All right. So that would be t over 2. So t over 2 times the square root of 1 plus t squared plus a squared, that's just 1 over 2, natural log of u. A few things to note. This is literally just what we got done doing. This is a secant cubed problem. This would end up being our secant cubed. So we could have done this in our previous one as well. But since we just got done doing it, I'm not going to do it again. All right. We have natural log of u t plus the square root of 1 plus t squared. Okay, and we're taking this from x to 0. All right, so plugging in x, we get x over 2 square root 1 plus x squared plus 1 over 2 natural log of, that's a 0, okay, natural log of x plus square root 1 plus x squared. Okay, so that's that one plugged in for x, so minus, now 0. Okay, if we plug in 0, this becomes 0. And this one here is 0 plus 1. So natural log of 1 is also 0, so it's just all minus 0. So we end up with this function. Our function, s of x, the distance of our arc length can be just described here as x over 2, square root 1 plus x squared, plus 1 over 2 natural log. Now, this is technically an absolute value, but because x is from 0 onwards, I don't really need it. So x plus square root 1 plus x squared. This is our generic function. Now I can find how long is the arc length starting from 0 to 10. Well, plug in 10, we could get the distance then, because we found it. This is describing that. Okay, but again, it has to start at this initial starting point of 0. If it starts at anything else, then we don't know. But if we wanted to find, like, from, say, 1 to 10, all you'd have to do is find the distance from 0 to 1 and subtract it from 0 to 10. So realistically speaking, it's not really that much of a restriction. Because again, let's say the arc length here, if we find the distance here from 0 to 1, and from 0 to 10, just taking this portion off would give us that distance. So, you know, that's how we work around it. Anyway, that is our arc lengths. And again, it's not that bad. It's just bad because the integrals are bad. So don't let arc length scare you. Just be aware that, hey, these integrals can be a little bit of a challenge. But it's good practice anyway, because these aren't going away. And let me tell you, they keep coming up. They're going to be coming up in the next section too. After this test, it's still in the next unit. So you're just going to have to get used to it. Anyway, thanks for watching.